Welcome to this video on reflection and refraction. We're going to cover a lot of topics today that all have to do with light. So I thought it would be nice to kind of go ahead and review what light is and how it travels. So we know that light travels in the form of rays, and these rays travel in a straight line until their pathway is interrupted by something. And so in reflection and refraction, these light rays are bounced off or refracted as they pass through different mediums. So the mediums we're going to deal with today include air, water, things such as glass, metal, even leaves. And so this is something that you can actually see in everyday life. It's a really important principle of physics. So we'll go ahead and start with reflection. So reflection, as you can see in this diagram, is when light hits an object and bounces off. When light hits an object, it hits at a certain angle known as the angle of incidence. On flat, hard surfaces such as a mirror or metal, this light is reflected at the very same angle that it hit. So the angle of incidence and the angle of reflection are equal to each other. You can see below an example of this reflection, which is also known as specular reflection, and that's on a hard flat surface. On surfaces that are a little more rough, such as a leaf with water on it, diffuse reflection occurs, and while the incident angle hits that surface, that will not equal the angle of reflection. Rather, the light, as it hits a rough surface, is bounced off in many different directions, as you can see. This allows rough surfaces to be seen from any angle, whereas hard, flat surfaces, to see the reflection, you have to stand at a particular angle. So some examples of reflection in everyday life. Here on the left, you can see this boat. This is a great example of specular reflection. And because of this, the water, because the water is so still, it's acting almost like a mirror, with the light being bounced into the viewer's eyes at a very same angle that the angle of incidence hit. And so because of this, it acts as a mirror, and we can see a perfectly mirror image of the boat. In rough water, we see an example of diffuse reflection. In this example, we can still see the outline of the boat, but it's a little more spread out and less clear because of the diffuse reflection. So those are some good things to remember. We're going to go ahead and continue into refraction. Refraction occurs when light passes through a material, and this changes the speed of light. So the materials that work and interact with light to refract have to be transparent, which means light has to be able to pass through. So dark materials can reflect, but for something to be able to refract, it has to be transparent or somewhat clear. Some examples of this are things like glass, clear glass, water, even diamonds are all great examples of refraction, and we're going to see all of those in this PowerPoint today. So normally light travels at a speed of 3 times 10 to the 8th meters per second in air. But as it interacts with different materials, it will slow down as it interacts with the different structure composition and atoms that make up the different types of materials. And because of this, the angle and the index of refraction are different for each material that you use. Materials that are more dense tend to refract at a higher degree than those that are not as dense. In physics, something called the index of refraction is used, and this is a standardized method to calculate refraction in different materials. And like I mentioned earlier, this is different for each material. So this equation, n equals c divided by v, is how you would be able to calculate that. To calculate n, you'll take c which is always going to be 3 times 10 to the 8th meters per second. And you'll take that divided by the observed speed of light, and that's going to be whatever the speed of light passes through the material that you're measuring, and that will give you a value of n. Once you have the value of n, you can calculate the angle at which the light will refract out of that material as it passes through. So as you can see in this image below, the light is hitting, it's being slowed down, so its angle is being changed as it passes through the glass, and then it passes back through the air and continues on its way. Using this equation for the law of refraction, this is also called Snell's law, you're going to need to know several different pieces of information, including N1, which is the index of refraction for the medium that you are first, the light is coming from, N2, which is the index of refraction for the medium that the light is going into, as well as theta 1, which is the incident angle, and theta 2, which is going to be the refracted angle. So take notes of that, and we're going to go ahead and use this in this calculation example. Feel free to pause the video if you'd like a minute to solve these, and then I'm going to go ahead and walk through it. Okay, so we're going to go through the first question. It asks, what is the index of refraction value on a piece of plexiglass if the observed velocity is 1 times 10 to the 8th meters per second? Okay, so remember this equation, n equals c over v, is what we're going to use to find the index of refraction value. If we simply put in 3 times 10 to the 8th, which is the speed of light in air, divide that by the speed of light in the plexiglass, which is given to us, we get the value of 3. That's going to be our index of refraction value. Okay, the next example says use the value calculated above to find the refracted angle given that the n of air is 1 and the angle of incidence is 30 degrees. Remember, the angle of incidence is the angle that light is coming from when it first hits the material. As it's coming from air, it hits at an angle of 30 degrees in this example. So this is going to be the equation we're going to use. We know N1 is simply 1 because it's air, and that's given to us right there above. We know 30 degrees is given to us as well, and we have 3 from the example above. So if you rearrange this equation to solve for theta 2, you can just go ahead and solve that to get theta by itself and put that in your calculator. And that's going to be how you set that example up to solve. So pretty straightforward once you get the hang of it. Okay, hope those were helpful. Here's some fun stuff of refraction in everyday life. I'm sure many of you have seen water tricks like this one done. That blue line is the true path of where the pencil is going to be. But it's seen as if it's broken in two right here because the light is refracted, and that changes the angle that the light passes through the water, and so it makes it appear as if it's broken in two. Okay, this diagram, if you'd like to take a look at that for a second, kind of explains what's going on as the pencil is down in the water and the light is being refracted at an angle that makes it appear as if it's broken. Okay, we're going to go ahead and move on to another principle, which is called the critical angle. This incorporates refraction and reflection. The critical angle occurs when the angle of incidence is at the angle that causes the angle of refraction to be at exactly 90 degrees. Okay, the diagrams below will help you visualize what's going on. In the example on the left, the incident ray is not at the critical angle, and because of this, as light passes through the medium, it's refracted out the other side. However, if the light hits at a certain critical angle, as seen in the example on the right, all the light that would be refracted is actually at a 90-degree angle, perfectly parallel to the edge of the medium. And because of that, the light is not escaping, or rather it's being reflected back in to the medium, as you can see. So in a case like this, all of the light that would be leaving is going to be trapped inside the medium. Some of you may have tried things at home, such as playing with lasers, and if you've ever tried using those, you'll notice that at certain angles, the laser can actually be reflected inside glass and plastic, whereas at other angles, the laser will shine right through. This is a great example of the critical angle. In every example that you'll use the critical angle, this deals with light passing from a denser medium to a less dense medium. Remember that. It's going from something more dense to something less dense. To calculate the critical angle, you'll use the equation circled, and that is in red. That's to find the theta critical. So critical angle is equal to the inverse sine of n2 over n1. And remember, n is the index of refraction. Okay, and you'll see some more explanations here on the slide of what you'll use to determine n1 and n2. n1 is equal to the medium the light travels in, and so that's going to be the medium, as you can see here below, that I just circled, that the light is hitting the edge of the medium, whereas n2 is the medium on the other side. n1 is the denser medium, n2 is the less dense medium, if that simplifies things. Okay, take another minute. Feel free to pause the video to work through this calculation example to make sure you understand how to calculate a critical angle. Okay, so we're going to go ahead and use the equation we just learned. We know that the n value of air is 1, and the n value of a diamond is 2.419. So if you plug all of this into your calculator, you're going to get 24.4 degrees. And that's your critical angle. Something to note is light that hits at any angle greater than 24.4 degrees in this example is going to be reflected inside of the medium. Light that hits at an angle less than the critical angle, in this case 24.4 degrees, is going to be able to exit the medium and leave. Some uses of the critical angle. I mentioned this before, but diamonds have a critical angle that allows them to reflect much of the light that enters in through the medium, and only at certain angles can the light leave the diamond, and because of this they're so sparkly and shiny. Another very helpful use of understanding the critical angle is actually in fiber optics, as you can see a picture of. Fiber optics are used in telecommunication, and they use light signals to transfer data. Because none of the light escapes through these fiber optics, all of the information is able to be transferred in a very efficient, fast way because it's traveling at the speed of light. So it's super useful, and you can also go ahead and study any applications to medicine or a lot of other up-and-coming technologies that take advantage of the critical angle to transfer information. Here at the end of my slides, I just included my works cited if you'd like to learn any more about that. I appreciate you taking the time to go over this slide with me, and I hope that was helpful. Thank you.